Okay, welcome to example 10. This is an Atwood's machine problem where we have mass m1, which is a larger mass than m2, which means m2 is going to move upwards and m1 is going to move downwards, and we need to determine an expression for the acceleration of the two masses. Now there are two ways to solve this problem. You can solve this as a system, which is quite quick, or you can solve them individually if you have to find the tensions. I'll solve them individually. Just so it's a little bit longer, but it also allows you to find the individual pieces like tension. So first, let's draw a free body diagram for each body. So we have M1. We have a force going upwards, which I'll label as T. And we have a force going downwards, which is the force of gravity, Fg1. Then if we look at body M2, we have also a tension. We'll assume that tension is the same as this tension on the other side. And we have a force of gravity 2 going downwards. Now once again, we know that M1 is larger than M2, so therefore this will accelerate downwards, and body 2, M2, will accelerate upwards. So now let's proceed on to solving each individual body over here on the side. So let me write down over here mass M1, and what we're going to do is we're going to sum the forces along a chosen y-axis. Now you can put your y-axis up or down. It's really up to you. Normally we choose up, so we'll just stick with up, and that means that the net force is actually downwards because there's an acceleration downwards. So what we're going to do is we're going to write m times negative a, and remember this is m1. Forces that are resulting in this net force of negative ma is the tension up and the force of gravity down. So over here we have minus Fg1 equals negative m1a. You can replace the weight with T minus m1g equals negative m1a. So hopefully you'll see that we now have an equation that has T in it as an unknown and A as an unknown, and we'll assume that we know M1 and M2 because that's what we had to find in terms of M1 and M2. So let's then move on to M2 and do the same thing. So we have mass M2, and we are going to sum the forces in this, sum the forces in the y, equals M2a, and the acceleration is upwards. We're still choosing our y-axis to be upwards here. So summing that forces in the y direction, we have tension up minus the force of gravity 2 down results in a net force of m2a. So tension minus m2g equals m2a. And once again, we'll see that we have tension as an unknown and acceleration as an unknown. So we need to eliminate the tension so that we can find the acceleration. And really we just need to write tension by itself. For example, T on the left-hand side would be m1g minus m1a, and then we're going to substitute into above equation. So what we'll get is m1g minus m1a minus m2g equals m2a. And now you'll see that we have two unknowns. Actually, no longer two unknowns. We only have a as the unknown. So we need to collect like terms. Put this m1a over onto the other side. We get m1g minus m2g equals m1a plus m2. Oops, let me correct that actually. That should be plus, oh, I had it right, m2a. And then we'll collect like terms. m1 plus m2 times a equals m1g minus m2g, and we get the acceleration is m1g minus m2g all over m1 plus m2. And you could rewrite that as m1 minus m2 times g all over m1 plus m2. So that's the answer for solving them in separate bodies. But let me just quickly show you how to redo this problem in a very fast way using summing the forces in one axis. But this will only get you the acceleration. So let me erase everything here. Okay, I've erased what I needed to and have the free body diagrams drawn over here. And what I'm going to do is look at this as a sum of forces along a system. So we have two bodies, M1 and M2, and we're going to consider this as a system. So maybe it might be easier to visualize this in one line. So we're going to consider an axis that kind of goes like this and down like that. Or maybe it'll be easier if I just actually show it all in one single line. So let me redraw that. So here I've done a free body diagram and just drew them, basically put M2 and flipped it up on the side, and M1 flipped it up on the side, so that you could look at this as basically here is your x-axis going that way. So maybe it's a little bit easier to visualize. And what we're going to do is consider a system that includes basically all of these bodies in here, these two bodies together. So if I sum the forces of the system, that will be equal to now the total mass of the system, which is M1 plus M2 times A. And now if you look at this, we're looking at the forces, the external forces that are acting on the system. So that would be M1G, which is externally acting on this one, minus M2G, which is going in the other direction. Now you might be asked, what about tensions? Well, tensions are inside of my dotted system, so they're actually called internal forces, so they in fact would cancel with each other out. And so this would be equal to M1 plus M2 times A. So look at this. It's really the difference between the two weights that causes this net force, and that will result in an acceleration times the total mass. So once again, you have A equals M1 G minus M2 G all over M1 plus M2. Same thing. You could think of this as delta M times G divided by the total mass. That's another way of looking at it. So there's another way of doing the same problem.